All right, hi there. I am going to turn on the live stream on Discord too, just in case somebody is checking and want to watch it live. Okay, so there we go. So I am live streaming both in Discord as well as in YouTube, just like a usual lecture. Um, but nobody is really kind of expected to be watching this live, but I just want to make sure that if anyone does, it is available. This particular video is to answer the question of why can't an edge be revisited on line 13 in Dijkstra's algorithm in one of the exams that we examined. The logic of this algorithm is pretty much the same as the one that we talked about in class, the one that we have in the modules. So it applies to that algorithm as well. So now, why is that the case? So I got the explanation in one of my mouse pads. So let me go find that mouse pad first. It's got to be somewhere here. Yep, I found it. All right, so I can paste the text, of the mouse pad, which is here, onto Discord and pin it, in case anyone wants to just kind of read the text explanation. But for now, I'm going to explain, why that is not possible. So what we'll do is we are going to come up with a hypothetical graph. Okay, there we go. So and we are going to look into a particular edge, okay, which is P to Q. Okay, so this particular edge is the first one to be revisited, okay, because if we claim that at least one edge is revisited, then there has to be one edge that was first revisited and with other edges possibly revisited as a result of this. Okay, so we identify this one as the very first one. But in order for an edge to be visited on line 13, if you look at line 13 here, they have to be incoming edges to vertex V, and vertex V in return is chosen on line 11, which means it has the lowest L value, and we also know that V has to be in Q in order to be selected here. Okay, so we know all of that stuff. So what we'll do is we will say that the first time, when we pick Q out of Q, the lowercase q out of Q, okay? So we say, first time Q is chosen from uppercase Q, we'll use L1 as a constant to remember the L value of Q at that time. Okay, so it's just, we're just freezing, that particular value and call it L1 so that we can refer to it later. But the fact that this is chosen, in that particular iteration of the while loop, we will also use Q1 to be the Q at the beginning of the while loop when Q is about to be chosen. Okay, all right. And then what we'll do is we're going to use Q1 to oh, we got that already. Okay, so we have now remembered a few things. Okay, so we basically say, okay, since lowercase q was chosen from Q on line 11 in one iteration of the while loop, we just say, okay, let's freeze the value, of L of Q at that time, and we know it as L1. Let's freeze the set Q, uppercase Q, and call Q1, from now on. Okay, so that's okay. I mean, we're just taking a snapshot. We're taking a group picture of the configuration of the algorithm at that point in time. Okay, so later on, we have some other iterations of the while loop. Things got updated, but eventually, because PQ as an edge was revisited on line 13, that means Q, lowercase q, somehow got back into the set Q in order for that to happen. because otherwise, lowercase q can never be chosen again on line 11. It has to be put back into uppercase q at some point in order for it to be chosen. Okay, does that make sense? All right. So, so we are gonna we will basically use that to kind of these vertices. Okay. PQRST. So we'll call T is already used. UV W X Y. Okay, we'll call this Y. Okay. All right. So we now say that there has to be a path from vertex R to some vertex, we'll call it Y, in Q1 minus Q itself. Okay, because because otherwise, this whole thing cannot be triggered. There's no way that R would be considered, which trigger the edge QR to be considered, also. Okay, so there has to be a path from vertex R to one of the vertices in Q itself. Okay, okay, so we are almost done here. But we know all edges are non-negative. Okay, so that means the path, okay, the length of the path from R to Y is non-negative. It is greater than or equal to 0. Okay, because we know all edges are have a distance of at least 0. So that's pretty much the case. Okay, so combining that with the distance of the edge QR itself, so that means the length of the path. So I'll just use length here, KLEN, from Q to Y is also greater than or equal to 0 for the same reason, because the edge QR itself also has a distance of at least 0. Okay, but now we have a bigger problem, because in order for Y to be in this set, in order for Y to be in Q1 minus Q, it was not chosen in that iteration, because we choose Q instead of Y in that iteration. So that means L of Y is at best, okay, equal to L of Q at that time. So that means L of Y is greater than or equal to L1. It can equal to, I mean, that it is possible for multiple vertices to have exactly the same L value in uppercase Q, the set. Okay, that's entirely possible. But when you add up these things, so when you add up L of Y and the length of the path from Q to Y, this is still at least as much as L1, which was the original value of Q when it was, I should put it, when it was first put into uppercase Q. Okay, or when it was, so when it was chosen the first time. Okay. But now in order for us to get into line 16, okay, to add Q, lowercase q back into the set Q, we are basically claiming that this value is also less than the old value of L of Q. Okay, and that is not possible, because you cannot have this value on the left hand side to be greater than or equal to, and also less than at the same time. So now we have our contradiction. Okay, so we say this is contradiction, and the contradiction is happening because we negated the theorem. The theorem basically says an edge cannot be revisited in Dijkstra's algorithm. So when we flip it, when we negate the theorem, it is then saying that an edge can be revisited in Dijkstra's algorithm. And as a result of an edge being revisited on line 13, and based on the logic of the algorithm itself, we now come to a conclusion that we have a contradiction. A particular value, being L of y plus the length of the path from Q to y, is greater than or equal to L1, and is also at the same time less than L1. L1 being the value, the L value of Q, the first time Q was chosen from uppercase Q. And this is when we perform this calculation, L of y plus the length of Q to y, that was calculated when Q was chosen the second time, when Q was put into the set Q again, okay, the second time, which then will lead to Q being chosen eventually again. Okay, but we are basically comparing the two instances of time that we're comparing is when Q was chosen on line 11 in the iteration in the first time lowercase q was chosen, and we are comparing it to the instant of time when Q lowercase q was put into the set Q on line 16 later on at a later point of the execution of the algorithm. So we're comparing those two particular instances of time and find a contradiction of certain things that cannot happen um, when you compare those two instances of time. So I hope this helps to answer the question, help you understand the algorithm a little bit better, and also, also to understand a little bit of, how to perform the analysis, when we have questions like that. But as I said, I cannot ask proof questions because proof questions cannot be individualized, and I do not feel comfortable asking questions that cannot be individualized in this particular final exam. Okay, so now that this is done, I am going to pin the text version, which is about the same thing as what I used over there in the written handwritten portion. It's just a little bit neater to look at for some people, so I'm just gonna save it and pin it into Discord. So give me a little bit of time here. Alright, so I've just saved the file, and I will pin it to the text channel of 2020 May 13th. So in case you're looking for it, it is there. Okay. I'm just writing the message that I'm pinning. There we go. Pin. Alright, there we go. So I got the text representation of all of this stuff here pinned. And I'm gonna move on to the counting problem next, but I got a few other things to take care of as well, so it might be a little bit of time before I get to the second video.